LeetCode 20. Valid parentheses might seem like a warm-up, but under the hood, it models real-world tasks like syntax parsing, code compilation, and validating things like JSON or XML. These are critical in systems where every character counts, so brute force won't cut it. Can we turn this duckling into a sleek, high-speed parser? Let's dive in. Let's kick off with the most basic approach, classic brute force. We'll keep stripping valid pairs from the string until either it's empty or we hit a wall. Let's drop into code and watch it unfold. First, let's handle an easy fail case. If the string length is odd, it can't possibly form valid pairs, so we can return false right out of the gate. To start reducing the string, I'll set up a loop that runs as long as we're making progress. That is, as long as we're removing at least one valid pair each time through. Inside the loop, we'll record the string's length before attempting replacements. This helps us know if anything actually changed after the pass. Now comes the pruning. We replace all valid pairs, and with empty strings. If the string gets shorter, it means we removed something, so we loop again. After that pass, we check whether the string changed. If it didn't, we're stuck. No more valid pairs to cut out, so we can stop looping. Once we've removed everything we could, we check if the string is empty. If it is, great, it was valid. If not, leftover brackets mean something didn't match. This brute force method runs in big O of n squared. For strings up to 10,000 characters, that's potentially 100 million steps. It's easy to write, but painful at scale. Plus, mismatched closes early in the string keep the loop spinning for nothing. Let's level up. Instead of cutting in waves, we'll process the string in a single pass using a stack to track open brackets. No need to mutate the string. We begin by creating a stack. As we move through the string, this will hold any opening brackets waiting to be closed, like a to-do list for matching. Then we scan each character in the string, one by one. This gives us tight control to evaluate each bracket as it appears. When we see an opening bracket, we push it onto the stack. That way, it's ready to be checked when we find its closing partner. If we hit a closing bracket, we check if the stack is empty. If it is, there's no open bracket to match. That means the string's invalid. If the stack's not empty, we pop the top. That's our most recent open bracket. We'll compare it against the current close to check for a match. If the popped bracket doesn't pair with the current close, that's a mismatch, and the string fails. We return false immediately. After we've checked every character, we look at the stack. If anything's left, it means unmatched opens, so the string's still invalid. Otherwise, it's good to go. This stack approach runs in big O of n, just one pass through the string, and we use up to n space for the stack. It's lean, fast, and perfect for interviews, especially at FAANG where clean linear logic is gold. We started with brute force, peeling off pairs like loose feathers. It worked, but barely. Then we tightened it up with a stack, a slick, one-pass solution that cuts time complexity from n squared to linear. That's a big leap in performance, especially for real-time parsers or stream-based validation. This isn't just about solving a LeetCode problem, it's about learning the patterns that great engineers reach for instinctively. Try this stack trick on other problems and keep swimming toward deeper optimizations. The pond runs deep.